Welcome back to another episode of Learning by Doing OpenFOAM. I hope you're doing great. Let me first and foremost thank all the people and community who basically interacted and engaged with the post I made over LinkedIn for the last episode of Learning by Doing OpenFOAM, where we talked about writing our own turbulence models in OpenFOAM, and also the kind of attention that I got over my YouTube channel. It was amazing, and it is absolutely. I got absolutely humbled, I'm very grateful and appreciative of that. I can also talk about maybe a little bit of a statistics and numbers, so that also you get an idea what I'm talking about. I do remember, like, when I started releasing Learning by Doing C++ video series. It was June of 2024. The initial feedback was sort of positive, but specifically the last 3 episodes of Learning by Doing C++, I do remember that I got something around, like, at highest, I got 900 or around 1,000 impressions over LinkedIn when I made a post about it. And then only the last episode of Learning by Doing OpenFOAM has surpassed that value by a large margin, by a factor of 4, like as 4 times as high as the highest value I had in Learning by Doing C++ video series. And it reached something around like 3,600 or 3,700 when I checked it a couple of days ago. It could be well above like 4,000 by now. It also showed itself in the number of people who basically followed directly my posts, so that now if I make a post over LinkedIn, they're going to get notified directly. And it also showed itself in a lot of connection requests over LinkedIn. And I also got some DMs from PhD students, people from academia, people from industry as well. And that is, as I said, very heartwarming, very encouraging for me. And I also witnessed same correlation over my YouTube channel as well. I got more likes, I got more subscriptions to my channel, I got more average view duration, I got more impression click-through rates. I got more of everything. Like when I take a look at, for example, my dashboard over YouTube Studio, everything is like green and increasing. And yeah, and that is, as I said, very heartwarming, very encouraging for me. I do appreciate and acknowledge the kind of support and the love that community is giving back to me. So this was the first time, and this is also reminding me of these gradient descent methods in machine learning applications. When you step, for example, in a specific direction, and then with a little step, and then you check whether you took the correct direction or not. but with the difference that this time around it's gradient ascent for me, because I'm ascending in that sense. So the kind of analogy I'm trying to make here very badly is that when you make these kind of content, and then you give a buffer time to basically see the feedback from the community, then you see that, oh, there's like a huge positive feedback from the community, and it means that probably you're stepping into the right direction. It doesn't necessarily mean that it's the best direction or it's the optimized direction, but absolutely it's a very positive and constructive. So this is the first point I wanted to make at the beginning of this episode. So the second point that I want to make is absolutely about the content of this episode. You remember the tradition is that we usually take a well-articulated problem that is stated in a thread in CFD Online, and usually we have 2 scenarios. The scenario number 1 is when there are already like possible solutions or comments from the specialists in the field, and there is a possible solution for that. But there is a need for a complementary material, so that people know why we do things the way we do things, extra explanation, or whatever you want to call it. The second scenario is that we don't have, the problem is stated, the problem is fresh, and nobody had time to basically write a possible solution for that. And then we jump in, and then we try to find a possible solution. We put the solution over the CFD Online thread, and then we also, as a cherry on top, we put that link also there. We say, hey, if you want to know more, if you want to understand why we do things the way we do things, then please click on this link and then watch the video. Okay, but today we are taking a little bit of a different approach. We want to touch something which is a little bit more fundamental. I was hesitant to basically make this video because, and I can also put the disclaimer right now, that this video is a little bit, touching the theoretical side and a little bit touching the practical side. We're going to talk namely about PISO algorithm, pressure implicit with the splitting of operators. So it has a very fancy name, but the method itself is very, very effective. It was first devised for transient and compressible and incompressible Navier-Stokes equations to deal with those problems. And it was basically first devised in 1984 by ESA. I absolutely encourage, if you are affiliated, if I can pronounce that, affiliated with a university, or if you have access to these scientific articles, absolutely go back and read the original paper of this PISO algorithm. If not, I was thinking about a workaround for this problem, and I was thinking like, and maybe we should take a look at something which is publicly available, because I was thinking that because of copyright issues, I can't show the original paper by ESA, but I can show something which is publicly available, right? That anybody can download it. And since we are talking about OpenFOAM, and as I said, we want to also see some practical aspects. So this means we want to see how the theory is basically translated into the source code of OpenFOAM. Then what kind of material is better than the PhD thesis of somebody who's one of the co-authors of the OpenFOAM itself? Of course, I'm talking about Professor Harvey Yasak, his PhD thesis from 1996. We're gonna actually touch the surface of the theory from that PhD thesis, and then we're gonna move along with the source code of OpenFOAM, and we want to see a little bit of the practicality aspects in OpenFOAM as well. As I said, a disclaimer: we just want to touch the surface of the theory, and also we want to touch a little bit of practical aspects. So we don't want to understand the whole theory, and we don't want to understand the whole thing behind every line in the source code of OpenFOAM as well, right? PISO algorithm, the corresponding solver in OpenFOAM is a PISO foam, and we're going to focus on incompressible, the simplest case, incompressible Navier-Stokes equations. So let's jump into the PhD thesis of Professor Harvey Yasak, specifically section 3.8, and you can also take a look at here, error analysis and estimation for the finite volume method with applications to fluid flows by Harvey Yasak, which was published in June of 1996. So let's go back to 143. Yeah. Discretization procedure for Navier-Stokes equations. Okay. The first equation you see here is basically the divergence-free condition. So del dot u equals 0. That's the continuity equation. The second equation is the momentum equation. And you see that there is no notion of density here. And there is an appearance of the kinematic viscosity. So there is no appearance of dynamic viscosity. So it seems like the right-hand side and the left-hand side are divided by density, right? But you see that there is no notion of P over rho here. And this is the notation that Professor Harvey Yasak is using, and it's also consistent with what we have in OpenFOAM. So I just want to directly jump into the practical aspect here. So let's go, for example, to tutorial, incompressible PISO foam. Let's take the laminar, the simplest one. No, let's take the case itself. Let's copy that. I want to go to my test case, and I want to copy, whoops, that thing here. Let's go inside. System, control dict, and let's go 0.1. 100 is too much. Let's go time steps. 1 time step is okay. And ASCII 6 general, yeah. This should be okay, but the point I want to make is here. Take a look at dimensions. This is kilogram, this is meter, and this is seconds. So meter squared per second squared. Is that the dimensions for pressure? Let's check it. So what is pressure? Pressure is force over area. So it should be Newton in an SI system, and then meter squared, for example, right? What is Newton? Is F equals MA, so it should be kilogram meter per square second divided by meter squared. So if I do this division, so this means that I'm going to have this kilogram per meter per squared second. So that's the units for pressure, right? But if I want to convert this into OpenFOAM language, it's going to be kilogram for 1, meter minus 1, and then second squared is going to be minus 2. But you remember that it was 0, 2, and minus 2. So let's divide this pressure by density, which is what? Which is kilogram per meter cube, right? Kilogram with kilogram is going to be gone. And I'm going to have a meter cube here, which you see a meter on the denominator, so it's going to be meter squared. So now you see that it's meter squared over second squared, right? So now you kind of understand that, so what is written here also translates into what we have in OpenFOAM as well. So we are not dealing with pressure itself, but we are dealing with the kinematic, so to say, pressure, which is the pressure divided by density. So that is very, very important to have in mind. And by the way, I can also run this to make sure that this case is running without any problems. That was an unnecessary step. Let's go back to the theory. Two things with this second equation, the conservation of momentum. First thing is that this is the nonlinear term. This is the convective term. If you take a look at the transport equation for a scalar field of phi, this term is going to be u phi. And the physical significance is that the phi field is getting transported with a velocity field. But when it comes to the momentum, because momentum intrinsically has that velocity in it, the physical interpretation sounds a little bit funny because velocity is getting transported by velocity field. So that's the first thing. This is the nonlinear term in the momentum equation. And the reason for that, if you discretize this, you're going to have quadratic terms in terms of velocity. You're going to have u squared instead of having u. So that's why we call it as a nonlinear term. The second thing is that you see that velocity terms here and a pressure gradient. So that is basically the, so to say, pressure velocity coupling that we have. We don't have a specific or a separate equation for pressure here, but instead we have the divergence free condition or the continuity equation. And then the beauty here is that we need to derive an equation for pressure, and then we're going to see how we can do that in a second. Here he mentions that, for example, this is how we discretize the convective term. If you don't know how this is done, I can give a general overview. You can start with chapter number 3 of this PhD thesis, which he basically talks about the fundamentals of finite volume method. But in a nutshell, if I want to very fast talk about these stuff, is that you start with the integral form of the conservation equations. You need two theories. You need the Leibniz theorem, because you want to play around with the derivative sign and with the integral sign. And then you need also the Gauss theorem or the divergence theorem as well, they call it. And that is when you want to convert those volume integrals into some finite summations over control surfaces of the volumes that you have, or the control volume that you have. And then after doing that, there are two assumptions that you need to make. The first thing is that if you want to calculate that surface integral, how do you want to approximate that? Do you want to only take the surface value at the center of the cell face? Do you want to only use that? Or do you want to use, for example, the points at the edges of the surface face as well? That basically gives you the degree of accuracy you're going to have for the first approximation. The second approximation is that once you pay attention to the discretization of the convective term and the diffusive term, you're going to see that you're going to need the values of that quantity over the faces for the convective term and the values of the gradient of that quantity over the faces for the diffusive term. And then you're going to understand that how you can relate the cell center values to the face center values. And that is basically the gives rise to interpolation schemes, how you want to interpolate stuff. And the interpolation is the second approximation you want to make. Do you want to make it like with 2 cells, with 3 cells? What computational molecule you want to use? What kind of accuracy you're aiming for? And these two approximations are separate approximations. And you need to be in harmony. You can't have like one in higher order. Like you make like the interpolation schemes as a third order, and then you approximate the surface integral with first order. They need to be in harmony, right? Okay. So far about that. So, but that's the story in a nutshell. So you're going to have discretized forms, which only rely on the P, the current cell that you want to write the equation for, and it relates also to neighboring cells that you have in your computational field. Finally, your system of equation is going to be a linear system of algebraic equations like this one, APUP plus A and UN, which APUP is the current cell that you're writing the conservation equation for, and this is the contribution that it gets from the neighboring cells. Okay. Then we go down. I'm going to skip these to be a little bit fast. Now we go to the derivation of the pressure equation. So this is basically APUP, and then we said plus AN UN, but that is an H operator on the right-hand side, and the pressure equation is the pressure gradient is also not discretized. So this is the semi-discretized form of the momentum equation, and this H, you can call it also as the H operator. What does it consist of? I'm sorry. What does it consist of? It consists of two things for now. The portion, which the contribution that comes from the neighboring cells, this contribution that comes from the temporal term, and there could be also other terms depending on the source terms, additional source terms. Since in our incompressible Navier-Stokes equations we don't have any additional source terms, then the H operator already is consisting of these two. Possibly the second term if you are having higher order temporal schemes. Then the discretized form of the continuity equation should look like this. That's the divergence of velocity should be 0. That translates into the S dot UF should be 0. And F stands for the value of the velocity over the cell face, not the cell center. And then, so equation 3136 is going to be used to express the U. So this is basically the equation. If you divide both sides by AP, you're going to have UP as H over AP minus 1 over AP of nabla P, or the gradient of pressure. So now you have the continuity equation and you have the momentum equation, but the momentum equation is expressing U in this case. Now, if you want to know the phase values, you can interpolate that. The phase interpolate of this equation is going to give rise to this, UF. So now you have the subscript of F, the same equation, but the interpolated values over the cell faces. And this will be used later to calculate the phase fluxes. Okay, bear that in mind. And then we're going to use equation 3140 substituted to equation 3138 because we don't have the subscript of F here. So this is not equation 3140 because that's over the faces. Probably he meant 3139 because this one is the one without the interpolation values. And it's going to give rise to this equation, which is famously called as the pressure equation or the Poisson equation for pressure. And if you discretize the right-hand side, it looks like this. Discretization of the Laplacian term on the left-hand side is also based on the standard way. You can go back to this section again. If you read chapter 3, you're going to understand what's going on. So we're not going to, as I said, we're going to touch briefly the surface of the theory here. If you are interested, just take a look at the whole chapter 3. So then finally, the discretized form is going to be APUPHU minus SPF, the values over the phases. And then you're going to have also the Poisson equation of the pressure. So that's the AP, 1 over AP or nabla P, and H over AP, right? So we're going to see that how this translates into OpenFOAM language. And then F is, of course, the phase flux, and that is basically S dot UF. And this is not a negative sign. This is like the old version of the thesis that I have. There's, if you want to, by the way, this is publicly available and you can download it. If you type, for example, Harvard US PhD thesis, you can download it directly from the Imperial College. There's a link for that. And there's a newer version of it with I think, LaTeX document. It is much, much better. This is the old version, but this is an equal sign. That S dot UF and UF is basically, this equation is being used for UF. If you substitute that, it's going to be this one. So now we go to pressure velocity coupling. So here he mentions about simultaneous algorithms, or what we call also as coupled solvers, where you basically solve everything simultaneously together, like the pressure and velocity. Of course, that comes with some negative sides. The cost of simultaneous solution is great. The number of operations is going to be increased, and also the memory requirements are also going to increase. So it's not very practical for large and practical CFD problems that you see, these coupled solvers. Now, the approach that we take is basically the segregated approach, which basically, as the name suggests, it's you're dealing with equations one at a time. So you solve them step by step, right? And we're going to see that approach also in translation of this statement into OpenFOAM language as well. And then if you're dealing with transient cases, the PISO algorithm, if you're dealing with steady state cases, the simple algorithm are going to be used, okay, for inter-equation coupling, of course. The PISO algorithm, first proposed by ESA, 1984, and then let us consider the discretized Navier-Stokes equations, and this is going to be the steps that you need to take for PISO algorithm. So these are the core ideas of PISO algorithm, very, very important. Pay attention, please. Momentum equation is going to be solved first. To solve the momentum equation, you need to know the gradient of the pressure, but you don't have the pressure. So what you do is that you use either a guess or the initial condition or the one from the previous time step. So that's what basically you do. So at this stage, you're solving for velocity components, and this is called as momentum predictor. So this stage is called as the momentum predictor. So after this solution, you are having an approximation of the new velocity field. It's not the actual velocity field in the new time step, but it's an approximation. Why an approximation? Because this velocity field doesn't satisfy the divergence free condition. It doesn't satisfy del dot u equals 0. So now using those predicted velocities, the H operator can be assembled. And then after that, you can assemble also the pressure, the Poisson equation for pressure. And then you can solve the pressure equation and this stage, and then you're going to get an estimate of the new pressure field. And this stage is called as pressure solution step. So in the next step, you are going to basically, you're going to correct the velocity field as a consequence of the new pressure distribution. So velocity at this stage is going to be corrected in an explicit manner. And the equation that we use to correct the velocity is the same equation that was up here, 3139. This equation in particular is going to be used. And you see that there are two terms when you want to correct the velocity. One term comes from the transport part of the neighboring cells, and the second term comes from the pressure gradient. And the heart of PISO algorithm is that you put more weight on the pressure. You basically say the error that appears in the velocity that I want to correct comes mainly from the pressure gradient. So you ignore basically whatever comes from this H operator or neighboring cells. So let's continue reading. So this stage is explicit velocity correction stage. And then here, it basically what I said, the change in pressure gradient, that's basically the first correction. And the second is the transported influence of corrections of neighboring velocities. And what we assume in PISO is that the latter part is neglected, like this HU over AP term. It is effectively assumed that the whole velocity error comes from the error that comes from the pressure gradient term. Of course, this is not true. It is therefore necessary to correct the HU term, formulate the new pressure equation, and repeat the procedure. But in PISO, as I said, this is how PISO works. You have implicit momentum predictor followed by a series of pressure solutions, and you have explicit velocity corrections. So that is basically the core idea. So, and within all those internal pressure correction equations, the HU stays the same. So the coefficients of these HU are not changing at all. So we're going to see this translation into the source code as well. So let's go back. So that's the PISO algorithm. Again, you have the momentum predictor. So let's take a look at, so this is the test case that we have. So now let's go to solvers. Let's go to incompressible PISO foam. Take a look at PISO foam itself. What did we say? We say, in theory, we said that we're going to have an implicit momentum predictor. That's where we have include U equation. We solve for velocities. And then we're going to have series of pressure solutions. And that's the inclusion within the PISO loop that depends on the number of characters you want to have, number of PISO characters. So you have series of solutions of the pressure equation. And you're going to have explicit velocity corrections. There is that stage in the code here. Of course, it's not being shown here, but if you take a look at the P equation, you're going to see that the explicit velocity correction also happens inside the P equation in this header file. So let's take a look at the U equation. So that's the general step. So now, as a summary, first we have the momentum predictor. Then we basically assemble this H operator. We assemble the pressure equation. We solve that pressure equation. That stage is called the pressure solution. We're going to get a pressure distribution. Then because of that new pressure distribution, velocity needs to be corrected. This correction happens explicitly with the equation 3139 that we showed. And I'm going to also show this equation because once we see the code, we're going to see whether it translates directly into that or not. So let's take a look at the U equation. Forget about the moving reference frame for now. What is the U equation? The U equation is a ddt of U. That's the temporal term. I can go up and show this. So this is the del U over del T. That's the temporal term. Then we have diff or divergence of phi and U. That's basically this the convective term, the second term. Then we have, again, forget about this moving reference frame. Then we have the effect from turbulence. We have div, def, ref. So div is basically short for divergence, right? And dev is short for deviatoric part of the stress tensor. And then we have REFF, effective, stands for effective. That's the effective stress tensor. You see that it comes from turbulence. So whatever, for example, in RANs, you have, like, from convective term, you're going to basically take some extra terms, which they look like stress terms. They can be treated as stress terms. We call them as a Reynolds stress tensor, and then you take them to the other side, and then you mix them with a stress tensor, and then you're going to have like an effective. And then you're going to, with Boussinesq, for example, Boussinesq approximation, you're going to say, hey, I have an effective viscosity that is basically the molecular viscosity plus some turbulent viscosity. This has sort of the same spirit. So dev is the deviatoric part of the stress tensor that basically concerns with only the shear components. You don't want to have the normal components because that is considered in the pressure. Those are the normal components. But you only need the portion which is coming from the shear stresses. Okay? And then we have extra source terms, if you have any, in FE options. So what we do here is sort of a little bit unconventional, but OpenFOAM allows it for you. So we have U equation.relax. So what is this relax in here? So I have two terminals. We can go to source. Can I grab for that? You see, it happens in a lot of places, but it should be somewhere in finite volume. Yeah, it should be somewhere in finite volume, for example. We can see that what that relax basically does. Like in FE matrices probably is a good starting point. Let's go here to finite, FE matrices. And let's go to FE matrix. And let's go in FE matrix.h and search for relax. You see, if you search for relax, it says relax matrix for steady state solution. But we know that PISO foam is sort of a solver. Let's take a look at PISO foam. What does it say? It says transient solver for incompressible turbulent flow using the PISO algorithm. And then it gives also the equations here, right? So going back here. So presence of this, because it's for transient cases, but here we say that for steady state solution. So alpha equals 1 is diagonally equal, alpha less than 1 diagonally dominant. If you don't know what that means, again, chapter 3 of Harvey-Ossack thesis, because essentially it means that when you want to numerically solve this algebraic system of equations, you need to have, with iterative solvers, of course, you need to have sort of diagonal dominance. So the elements or the coefficients on the diagonal need to be as big as possible compared to this summation of the all coefficients on other neighboring cells. And alpha is 0 means that do nothing. So you see that the relax is basically here. So let's take a look at fv matrix.c and let's search for relax. You see relax function here takes also an alpha argument here, but here we just say relax without any argument in here. So let's look for other relax functions. So I'm going to go next, and this is what it happens. So it basically first selects the what's it called, the field itself. So the psi is basically the field, and then we have this relax coefficient, which by default it sets it as 0, and then it checks whether you have defined any relaxation factors in your. Normally it happens in system FV solutions. You add it in there. So if you have defined some relaxation coefficients in there, it's going to substitute that into that relax coef. But otherwise, it's going to be defaulted into value 0. And if you go back here, the value 0, where's the, yeah, here's the relax with the alpha value. The value which is less than or equal 0 is going to just return. So this u equation dot relax currently is not going to do anything. Why? Because in if I go back to my we went to test case. If I go here in system and FV solution, you see that we don't have any relaxation factors here defined. So in essence, u equation dot relax basically does nothing. So let's go back to incompressible PISO form. Whoops. And let's take a look at the u equation again. So we relax the system, and we saw the definition, how it goes here. So in essence, this line is basically doing nothing. And then we have FV options, constrain u equation. So this is if you have extra source terms. And then you see that there's an if condition here. It says if PISO momentum predictor, then solve. There's no solution. This is just assembling of the u equation. Here, the first time that we say, hey, we want to solve this u equation or the momentum equation. So that is solve u equation equals to minus FVC. That's the finite volume calculus. That's basically the explicit term. It's not going to be sort of added into the equation, but it's going to be a source term in this case, minus FVC of grad P. So we have all the source terms here other than the pressure gradient. There is no sign of pressure gradient in here. And the pressure gradient basically shows itself here in the solution for the momentum predictor. So normally here you see that in the steps, we said that we solve the momentum equation to get an approximation of the new velocity field. But you see that there's so let's just go to run. It was the sorry, I can go with test case, that's easier. This one, and then log of PISO foam. So here you see that we have ux and uy. Take a look at this. If I go to FV solution, and here, if I add momentum predictor as no, and I save this, all clean this, and all run this, you see that in PISO foam now, there's no sign of solving for u equation at all. So that is why we have this sort of check in there. Oh, sorry, it was the same terminal I was using. So let's go back and turn it back on. So this is something that you can play with, the momentum predictor. Either you want to have it or you don't want to have it. But you see that in the theory, here it says that, hey, probably it's a good idea to solve that, to get a nice first approximation of the velocity field. So now let's go back again to incompressible, PISO foam. I think u equation was finished, right? Yeah, we solved the u equation and we get an approximation of the velocity field. So now going back here, you see that again, two things we can see here. The first thing is that we had one implicit momentum solution, and then we have a series of pressure equations followed by explicit velocity correction, which we don't see that explicit part. I'm going to show it in a second. And the second thing that you are seeing here is that the segregated approach. So we are dealing with one equation at a time. We have the momentum equation, and then we go for pressure correction. So now you see the translation of the theory or whatever was in Professor Yasak's thesis in the code itself as well. Now let's jump back into the P equation, the pressure equation. Here things are a little bit lengthier or maybe a little bit more complicated, but we're going to break it down and it's going to be easy for you. So the first thing is RAU, which is defined as 1 over U equation A. That sounds like this term here, 1 over AP. 1 over AP. That's the term that we are looking for. So this 1 over AP is actually 1 over U equation dot A. What this dot A means is actually the reciprocal of the main diagonal element in the momentum equation. And you see that the A is taken from the U equation. U equation, we assembled it in the previous, when we included the U equation in PISO foam, we assembled already the U equation. And now we want to calculate those 1 over AP, and AP is the coefficient on the main diagonal. That's the cell that I'm writing that conservation equation for. So this is how I initialize that. That term is called as RAU, or the reciprocal of AU. That's in theory, we call this 1 over AP. And then we have H by A. That is easy because here we have H by A. So we need the H operator divided by AP. So let's see how this one is constructed. So neglect this constraint H by A. So we have RAU, this is 1 over AP times U equation dot H. Again, we are taking H from the assembled U equation in the previous step. And then we are passing in U and P here as well. And we are passing it to the function constraint H by A. We're not going to deal with that for now, but bear in mind that we're going to come back to this later. Then we have phi of H by A as simply the flux of H by A. That definition is very simple, along with some moving reference frame stuff, which we say that we don't want to worry about that. We just neglect that. And then we have this make relative, again, a portion with moving reference frame. We don't want to deal with that. No extra complications. The next thing we have is adjust phi. What we are passing here is phi H by A, we are passing U, and we are passing P. So it doesn't, probably you don't see the essence of it right now, but I can also show it right now. So let's go here in source and grep minus RL of adjust phi. You see that in finite volume, in CFD tools, in general, we have adjust phi and adjust phi dot C. So what is happening here? What is happening is that I'm sending a phi that's actually not a phi, it's a phi H by A. You see it here. I'm sending a phi, I'm sending U, and I'm sending P, the velocity and the pressure. And what it does here is that it checks the mass balance, the mass in, the fixed mass out, depending on the conditions that you have, the boundary conditions. Some amount of mass is basically restricted by the user or determined by the user, that it has to be the output mass. Or some of the mass could be adjustable if you have, for example, inlet outlet conditions that you can basically, balance things with it. So what this section basically does, again, as I said, we want to touch also this, we don't want to understand every line of the source code, but the main ideas are important. So here we initialize these three things with 0, so mass in, mass out. The mass out has two proportions or two contributions. One is the fixed mass out depending on the boundary condition, and the other one is the adjustable one, as I said, for example, inlet, outlet, and stuff like that. So what it does is basically it takes the boundary values of the phi, and then for boundary values of phi for every patch, it's going to have the boundary values for velocity and the boundary values for every patch for phi. And then what it's going to do is going to check whether you are having like positive or negative inflow or outflow. And depending on that, it's going to like add or subtract from the mass in and mass out. Finally, what it's going to do is is going to calculate the total flux in the domain used for normalization. And then you have reduce operations here because in parallel cases, then you need to do these reduce operations. Again, if you don't know what reduce operations are, I would advise you to go back to Learning by Doing MPI video series, where I talked about reduce operations in collective communications chapter. We talk about these reduce operations. It basically is easy and straightforward. Okay, then what it does, it basically it defines a mass correction factor, and then it basically checks for a condition here. Either you're going to have a mass correction which is calculated based on this formula, so mass in minus fixed mass out divided by adjustable mass out, or if this condition doesn't satisfy, then it's going to tell you this error, that continuity error cannot be removed by adjusting the outflow. So what adjust phi does is basically this adjusting the outflow. It's going to scale basically your phi over the boundaries with this mass correction factor. So assume that this condition is fine and we are not going to hit this fatal error. And then what it does is going to, again, for the boundary values of phi for every patch, what it's going to do is, like, again, access UP and phi p, the values over the boundary patches. And what it's going to do is finally it's going to scale it. You see that this star equal mass correction factor. So it's going to scale those phi values over the boundaries. So that's what it means, this adjust phi. That's what this adjust phi function does. And then, of course, it returns a Boolean here. So in this case, it's going to return this mag of this condition and then mag of that, and then this. So again, so we have adjust phi here. And then what we need to do is update the pressure boundary conditions to ensure flux consistency. Again, constrained pressure. For now, probably it doesn't make sense if I show these. We need to first basically, or I can show it right now as well. So let's go to source and constrain pressure. Again, you see that in finite volume, in CFD tools in general, we have constrained pressure. And this constraint pressure.c, as it says also here, it says we want to update the pressure boundary conditions to ensure flux consistency. Okay, so what it does here, everything here is const reference other than the value of the pressure. So here you see that the pressure is just a reference. It's not a const reference. And the reason for that is because you want to correct the pressure boundary conditions, the pressure values over the boundary conditions, over the boundary faces. So everything else is basically accessed through the const references. And then what you do, basically, you go over the pressure boundary faces. And for every patch, you basically want to update this normal gradient, the SN grad. And this is how you update it. So that's basically in a nutshell. If you don't want to dig deep into what is actually done here line by line, it is simply update the pressure boundary conditions as this simple comment says. Because we are going through the pressure boundary phases, and for every patch, we are checking whether we can change, whether we can update. You see that this is updatable SN grad. So if we can update that surface normal gradient term for the pressure boundary condition, yeah, we put it there. And then we have non-orthogonal pressure corrector loop. And then again, if you don't know what this non-orthogonality stuff is, please go back to the theory again, to this chapter 3. Professor Yosak actually has a dedicated version to those non-orthogonal corrections. Like there are like 3 proposed mechanisms how you need to sort of distribute it into a term that is parallel and a term that is not parallel, and it needs to be approximated. But anyways, assume that we don't have, and actually we don't have in this case of porous something that we had as the example that we were solving, we don't have this non-orthogonal corrections. So the P equation is getting assembled, and that's basically this. This is the Laplacian of RAU and P. Again, you can also see it here. This is RAU, which means 1 over AP. We already saw that. That is constructed based on the 1 over U equation dot A. And that's the Laplacian term. And on the right-hand side, what do you have? You have H by A. And since we are balancing fluxes, you're using this div of phi H by A, right? So that's the pressure equation. We haven't solved it yet. We just assembled the pressure equation. And then here we have a very strange thing here. We have set reference, P ref cell, and P ref value. So let's talk about the essence of this. So if you take a look at this incompressible Navier-Stokes equations, you see that pressure, there's no notion of pressure in this equation. You see the relationship between the velocity terms and the pressure gradient. So that means in incompressible Navier-Stokes equations, the pressure, the absolute value of pressure doesn't have any meaning. So what matters is the gradient of the pressure. So this means that this system can have billions of solutions. So we could have a system with pressure of like 1 bar or 1E5 Pascal, and then we could have a pressure gradient of 2 bar, and then we're going to have a flow because of that pressure gradient. Or we could have the same scenario with the pressure, instead of 1 bar, we could have a pressure of 10 bar and the same pressure gradient of 2 bar. And then again, we're going to have the same flow. So in that case, this system cannot be solved because there's like a singularity in there. There are like billions of solutions for our system, right? So what they do is that they add a reference point in there. So they specify the value of the pressure at one computational cell. Usually they put a 0 in there. And I think we also saw it in our test case. In system FV solution, you see that P ref cell is 0 and P ref value is also 0. So you specify the pressure value in one computational cell because you want to make sure that your system is actually not having any singularity, and there is but you know that the absolute value of pressure doesn't have any meaning in incompressible flows. So that is because we have the term of pressure gradient, or we have the appearance of pressure gradient and not the absolute value of pressure. So let's go to incompressible again and the PISO foam. And where were we in P equation? We were. So this is what this line basically does. And we have at this step, basically we solve the pressure equation. And yeah, this is only where at the final iteration it needs to save those values, not the intermediate ones. And then if it's the final non-orthogonal iteration, in our case, in the example that we saw, we don't have any non-orthogonal corrections. And I'm going to show it where you can set it. But finally, what you do, you need to also update your phi, your fluxes as well. And that's this equation. That's the translation of this theoretical equation here. So this UF H by A minus 1 over AP nabla P. So that's basically phi H by A minus P equation dot flux. That's the second term here. So you update your fluxes. And then what you do is that you have continuity errors here. I'm going to go back here. Let's go to source and look for that continuity errors. You see that in finite volume, in CFD tools, incompressible, you have this continuity errors. And what it does is basically very simple. Since you updated your phi values in the previous step right here, now it's going to use those updated phi values based on the new pressure field. It's going to use that to calculate the divergence of that phi, and that's going to be your continuity error. So that is that the del dot u equals 0, but this is not 0 right now. It should have some value, but that is basically the translation of del dot u, this term here, divergence of phi. And then the sum local continuity error is that you take the delta t and then you take the magnitude of the continuity error only the positive portions, and then you take the weighted average with the significance of each computational cell. So weighted average is like you take an average, and if you have a bigger computational cell, that is going to have more impact on the average. If you have a smaller computational cell, it's going to have less impact on the average. And you take the value of that. So that's how you calculate the sum local continuity error. Then you have the global continuity error, which is the same thing, but without having this mag here. So you're only taking the continuity error. And then the cumulative error is actually the summation of all the global continuity errors. So there could be positive values, there could be negative values, and the cumulative one is the summation of positive or negative ones depending on the conditions that you have. And then what basically OpenFOAM dumps out, this is after each pressure correction equation, you see that these continuity errors are dumped out. So that's, again, another part. And then finally, this is the step that we were talking about here. Explicit velocity corrections. At this stage, we said equation 3139. So let's go back here. This is equation 3139. UP is going to be corrected with H over AP. That is H by A minus 1 over AP nabla P. And that is RAU, that is 1 AP. And this is FVC grad P. That is nabla P. So that's the gradient of the pressure. And then you correct the boundary conditions, of course, and if you have any extra source terms with FE options. So a very beautiful translation of whatever we see here in P equation. So P equation is being, let's say, this is being executed once. And in the second corrector, it's going to come back again. It's going to come back again. And it's going to go with RAU. So U equation dot A is not getting changed, right? Because we don't touch the U equation at all. But does it mean that this equation is going to be the same? Because RAU is not changing. And this phi H by A seemingly, it sounds like it's not changing because we have RAU U equation dot H. So are we basically solving the same system of equation over and over? To see that in a better form, let's take a look at what really happens under the hood. So I'm going to take this PISO foam and I'm going to go to my code. I'm going to copy this PISO foam here. I'm going to move this to custom PISO foam. Let's go to custom PISO foam. Let's grab -RL PISO foam and then xargs that into set of in place and then s of PISO foam into custom PISO foam, and I want to do it globally, and I want to also move this PISO foam to custom PISO foam.c. Let's go to make and files. Here I'm gonna put user app in because I don't want to mess up with the original solvers of OpenFOAM. And what I'm gonna do here is just to vclean and vmake and make sure that this solver is getting compiled. And on the other side, I can go back to my test case, and I want to actually change the system, the PISO foam. I want to change it to custom PISO foam. I want to use that solver. But here, in essence, we haven't made any changes, so we can test it if it works. All clean and all run. And you should be able to see that the solver runs. It's essentially the same PISO foam as before. But what I want to basically do is to show you something nice here. So before solution of this pressure equation, what I want to do here is I want to show you, if I say P equation, because OpenFOAM uses this LDU format, let's type here diag. And before that, I want to also put something that shows that this is P equation dot diag. And I'm going to put an equal sign here. Of course, this should be diag. And then let's put an n line here. And then I'm going to do that, copy that billion times. I'm going to say upper. I'm going to say lower. And I'm going to say source. Let's see what's going to happen here. And I'm going to, I have to also change these. Otherwise, it's going to be very stupid. So upper, lower, and then source. I'm going to add this to the source code, and I'm going to run that or compile that. You see that it basically, I'm not going to go to the previous terminal because it's very small and probably you can't see it properly. So I'm going to go here. I'm going to go all clean. I'm going to go all run. And let's take a look at this custom PISO foam. Now you see that gajillions of stuff are being printed here. But first thing is that this was for 2 time steps, so I don't want to mess up things. I'm going to go back here, and instead of 0.1, I want to make my life easier and only make it for 1 time step, 0.05. So I'm going to go all clean again and all run. Let's take a look at this custom PISO foam. Now you see that this is the first pressure corrector that it starts, and we basically dump out the diagonal elements that we have 2048. Take a look at log.blockmesh. If you take a look at it, you see that the number of computational cells is 2048. And that's the main diagonal elements in that pressure correction equation, right? And then we have internal phases of 4000. Let's take a look at this log custom. Let's take a look at lower. You see that it has 4000 elements. These are the terms that are coming from the internal phases. And let's take a look at upper. You see that again here we have 4000 elements. And the main diagonal has 2048. Let's take a look at source terms, 2048. So our system is 2048 by 2048. So we have 2048 source terms, but the upper triangular and the lower triangular matrices or values are having 4000, and those are the contribution from the faces, right? Or the neighboring faces. So now we have these values for 2 consecutive pressure correction equations. So if you take a look at FV solution, you see that here we have 2 characters. So I want to see, after the solution of the pressure equation, is my system even changing at all? Is the pressure equation that I'm trying to solve, is it changing at all or not? Because we said that, hey, let me show it again. I think it was in solver, custom MP equation. What we said is that, hey, RAU is not getting updated, right? Because it's 1 over AP, and RAU times H is also probably not changing. So if these 2 terms are basically the same, then doesn't that mean that we are solving the same equation over and over? So let's take a look at that. So what I'm going to do is so if I grep for example, diag, you see that it basically shows me these 2 occurrences, but that is not good for me. So let's do a diag with minus A, and you remember that we had 2048 elements, but then we had also some extra lines here. So let's go here. So we have, for example, 1, 2, 3. I can add 3 lines extra here. So if I say grep minus A, and instead of 2048, I'm going to say 2051. So that's going to look for diag with that to make sure. And then look in log.custom PISO foam and put it in plog or plog1, for example. If I hit the return key, you see inside plog1, I have the first one from the first pressure corrector loop. So I'm going to go down 2048 lines, and then this is the end of it. And the second one comes from the second pressure correction, right? So I'm going to take these values. I'm going to use the X. So I'm removing all those stuff. I actually should have created one. Can I do it here? Probably I can, right? If I say touch p log 2, this should do it. And if I say VSB p log 2, and if I press the P button, now I'm getting the second portion. Now I have two P logs. One is from the pressure, one is from the first pressure correction, and the second one is from the second pressure correction. And I want to take a look at this P log 1. I want to compare it with P log 2. And these are the diagonal elements. You see that the system is not changing. The diagonal elements in the pressure equation are not changing. So now let's do the same thing with, let me just remove these values. Let's do the same thing with, where was it? Grep. So let's do the same thing. Instead of diag, I want to use upper. And instead of 2051, you remember it was 4,000 elements. So let's put 4,000, I don't know, 3 maybe. I'm not sure. So let's do that. If I do that, and if I go to in P log 1, so you see that, yeah, that is good enough. So I'm going to remove these. I'm going to go down 4,000 lines. And this is from the first pressure correction. I'm going to remove these. And these values are from the second pressure correction. I'm going to go to P log 2. I'm going to paste those values here, remove these parentheses. And now I want to compare these two. If I do a vim diff, you see that again, these values are the same. 4,000 lines are exactly the same. So the upper values in that pressure equation are also the same. Then what the heck? Is our theory right? Is the pressure equation the same? So let's do the same thing for lower values. So these are the lower ones. And I'm going to P log 2 to remove these things. Oh, I made it a visual block. That was a mistake. That was a huge mistake. I actually don't want to do that. Yeah. So now let's go to P log 1. And you see that these things are from the first pressure correction. I'm going to remove these. And these values are from the second pressure correction. I'm going to take that, VSP in P log 2. And I'm going to paste them here, remove these parentheses. And I'm going to save it, and I'm going to do a vim diff. So you see that again, 4,000 lines, which are exactly the same. These are exactly the same. And if you take a look at also upper and lower values, you're going to see that these values are also the same. So there is also a symmetry in the system as well. But this symmetry is not a rule here. So not all the pressure equations are going to be symmetric. If you have non-orthogonal terms and stuff, then you're going to have asymmetric systems. But in this specific system, because we have no non-orthogonality in the system, then we have the symmetry as well. Okay, so then the question is, okay, the matrix, if we are solving this system of AP equals B, so A is not changing because the upper values, the diagonal values, and the lower values are exactly the same in both pressure equations, pressure correction equations. So what the hell is changing? What the hell is changing? And the thing that is changing is actually the, let's take a look. It should be the source, right? But let's take a look. How many source values did we have? 2048. I'm going to put 2051. And let's just run this. P log 1. And these are the first 2048 values. I'm going to delete these. And this is from the second pressure correction. VSP of P log 2. And I'm going to delete all these values. And I'm going to paste those values. And I'm going to do this. I think I made a mistake. Yeah, I did because I was not supposed to do that. Okay, let's do the grep. That was a fatal mistake because I X'd it in Vim and I lost those values completely. So let's make sure that the plog2 is empty. I need to empty this to not make the same mistake twice. So I'm going to remove these and let's go 2048 lines down. I'm going to delete these. These are from the first pressure correction. I'm going to take, these are the values from the second pressure correction. And I'm going to go to plog2 and I'm going to, oh my lord, that is, okay, that basically shows that it's, I'm getting tired. So, okay, let's go to plog again. I lost everything. 2048 lines. Let's remove these. These are coming from the second one. I always press, okay, plog2. And let's paste them here. Save this. And now let's do a Vim diff. So here you see the difference. It took me ages to prove this, but I think it's basically worth it. But now you see that the source is changing. So if the source is changing, so this means that there has to be something happening with this VH by A and stuff, right? Because that's the only, if I go here in my custom PISO foam, you see that the only source that can contribute into that is basically this VH by A. And if you look carefully, then you see that we have this constraint H by A. And we send these values of U and P. And you already know that U is getting calculated here. U is getting corrected here. And P is also getting updated here after we calculate the pressure field. So again, we have constraint H by A. We pass in these U and P. The boundary values are going to get corrected in this H by A. Then consequently, phi H by A is changing because H by A is changing in this step with this constraint H by A. We haven't checked the function itself, but we can also take a look at it. So you see in finite volume again, CFD tools and general and constraint H by A, you should be able to see that what this one does. Again, you can take a look at it, what it does, but what it essentially does, it checks whether it's movable to avoid unnecessary like copying stuff. If not, it basically clones it. And what it does is basically, again, going through the boundary values of the velocity, and it checks if the boundary is not assignable, or if the pressure, if you don't have this specific pressure condition of fixed flux extrapolated pressure, then what it's going to do is basically put H by A at the boundary field at that specific patch to the values of the boundary field of the velocity. So that is basically, it's going to correct the phase values of this H by A with the values of the boundary field on velocity. So very nice. So now we saw how nicely the theory which was discussed here in probably not every detail, but you saw a very nice picture of how things are basically changing here. So at every time step, again as a summary, at every time step, we solve the U equation. If you have the momentum predictor on, we solve the momentum equation once with this explicit gradient of the pressure. We calculate some intermediate velocity field values. We constructed this U equation once, and now we go to P equation, and we have that series of solution of the pressure equation. And within those series, the U equation is not getting touched at all. So within these inner iterations of the pressure equation, the solution of the pressure equations, the U equation.A and U equation.H are not changing at all. So what is changing here between every pressure equation solution is not the left-hand side. So the diag values, we saw that all the coefficients are the same. The upper and the lower coefficients are all the same. But what is changing is actually the source term, which comes from the phi h by a. And you see that bunch of functions here that are taking u and p. And you know that u and p are getting updated. So pressure is getting updated after the solution of the pressure equation. Phi is getting updated. U is getting updated with a new pressure gradient. So they're getting corrected basically. And so h by a, which depends on u and p, you see here, it depends on u and p with this constraint h by a. So h by a is definitely going to change. Consequently, phi h by a is going to change. And then you also see that we have adjust phi here, which takes u and p. And these u and p are the latest u and p. So these are the u and the velocity and the pressure after the correction. So you see that adjust phi also takes a portion of those effects, and constrained pressure is also taking some of those effects, because here also it uses the pressure and the velocity. So finally, when you assemble the pressure equation, what is happening is that the source terms are going to change. And we saw those effects. Of course, it was very hard and time-consuming to show you those due to my inability and me being tired to be effective. But you saw basically that with the WimDiff, with very simple tools in terminal, we basically grabbed everything and then put those values and then WimDiff and compared those values together. And we saw that the only source of difference is coming from the source term. This video was very, very lengthy and long, but I hope it is worth it. And at least we saw the translation from the theory, or at least the surface of the theory that we saw in chapter 3. By the way, I also advise and encourage you to read the whole chapter. It's a very nice chapter. You're going to understand everything. And the nice thing about the thesis of Professor Harvey Yasak is that it also translates directly into the language of OpenFOAM. There's a huge correlation and synergy between the two things. I hope that you learned something about PISO algorithm, something a little bit about theory of it, a little bit about practical terms in OpenFOAM language, and I hope to see you in the next one.